Hey guys, welcome to chapter 2 in chemistry. Chapter 2 is going to be one of the most difficult chapters we talk about this semester. In chapter 2, we're going to look at the quantum mechanic model of an atom. Even if you've had chemistry in high school in your past, this is likely something you've never seen before. Or if they did talk about it in high school, they just kind of skimmed the surface of it and didn't dive deep into it. But since we're in a college chemistry course, we are going to dive headfirst into the quantum mechanic model of an atom. So what do we know about an atom up until this point? We know that an atom has a very dense region called the nucleus, and inside of this nucleus we find all of the atom's mass and its positive charge. So in there we find the protons and the neutrons. Scattered around the nucleus, up until now we've called this an electron cloud. But what we're going to spend the next couple chapters doing is talking about how incredibly organized that electron cloud is. It's a very intricate system, very thoughtfully put together. So that's what we're going to spend some time doing, is diving into that electron cloud. First thing that we're going to talk about is this very peculiar behavior of electrons. So electrons are technically incredibly small pieces of matter. But the behavior of those electrons, as we'll see very quickly, resembles less of a piece of matter and more of a wave. So that's going to be the first thing we talk about. Why do we talk about electrons? Why are we going to spend all of this energy and thoughtful process thinking about electrons? Well, much of the behavior of an atom is determined by electrons. So structure determines properties, and for us, we are incredibly interested as chemists in the electron. It explains the manner in which electrons exist and behave in atoms. So we're going to talk about where are they housed. We're going to talk about how they behave, why they do the things that they do. And then once we understand why the electrons do the things that they do, then we can circle back around and talk about an atom's properties. So why does water become less dense when it freezes? Why is carbon dioxide either a gas or a solid and it never enters into the liquid phase at standard pressure? So all of these properties that we observe all hinge on these electrons. So as I alluded to before, electrons behave in a very peculiar manner. So to understand how electrons behave, the first thing that we're going to talk about is how does light behave? What is light? And then we'll circle back around and see how that's similar or different than an electron. So light is not matter at all. Light is actually an electromagnetic radiation. Electromagnetic radiation is just a fancy word for, it's a couple waves. So we see this electric field that propagates up and down. We see this red magnetic field that kind of goes back and forth. So these two waves propagate perpendicular to one another. And when we study them as one entity, we call that electromagnetic radiation. So an electric field and a magnetic field that work together. Light is not matter. It travels in the form of a wave. And in a vacuum, it travels at a constant speed, and not something that you're going to need to know. We don't do any calculations with the speed of light. We've got a lot more on our plate that we need to focus on. So that's something that I don't really go too in depth with. What I do want to talk about, because this will be important when we start looking at some experiments that scientists did with electrons, what I do want to talk about is some characteristics of waves. So here we see a wave. The first thing I want to talk about is wavelength. So the wavelength is going to be the distance from two identical places on a wave. So it could be peak to peak, could be trough to trough, it could be midpoint to midpoint. Any two identical points on that wave, if you measure the distance between them, that's the wavelength. So something that has a really long distance between the peaks has a big wavelength. Something that has a short distance between the peaks has a small wavelength. The next thing I want to talk about is amplitude. So amplitude is going to be the vertical height of a wave. So the taller the wave, the bigger the amplitude. The shorter the wave, the smaller the amplitude. When you hear the word amplitude, you probably think of sound waves. So something that would be a really tall wave would have a high amplitude. It'd be really intense and loud. Something that's a small amplitude, short wave, really soft and quiet. Since we're talking about light, if we're talking about the amplitude and light waves, something that's a really tall wave would be an intense, bright light. Something that's a short wave would be a very dim, hard to see light. So it would be a small amplitude. And then the other thing that's not pictured on this slide, but we can still talk about, is something called frequency. So frequency is the number of wave cycles that pass a given point. So let's say my laser pointer here is the point that I'm going to stand at. Let's say I'm going to stand at that point for 5 seconds, and I would count how many waves go by. That would be a measure of frequency. So the number of wavelengths that pass a point in a given amount of time. So something with a high frequency, we would count lots and lots of waves going by. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Something with a low frequency would be less waves in that same amount of time. So 1, 2, 3. So high frequency, lots of wavelengths. Low frequency, just a few. A wave is described both by its wavelength and its frequency. So again, this is a formula that your textbook gives. It does some examples, some calculations with it. We're not going to do that. We've got bigger fish to fry. But I do like to put it up here just so you can start to see that relationship between wavelength and frequency. So what we see here is the product of wavelength and frequency equals that speed of light. So what that tells me is that as a wavelength increases, so if I have a really big wavelength, a really long distance between those peaks, that means the frequency is going to be very small. So let me draw some waves up here and do that. So here would be an example of a big wavelength. So wavelength would be really big, but the frequency would be really small. So if I stand here, I may only see a couple waves go by. If I look at something with a short wavelength, it's going to have a high frequency. So if I look at something like this, so in this case, it's got a really small wavelength, but the frequency would be a really high frequency. So if I stood at the same point and counted the number of waves that went by, it would be a much higher number. So there's an inverse relationship here. So inverse relationship, big wavelength, small frequency, small wavelength, big frequency. Okay. And then the one other thing that we will eventually talk about, and we'll throw in here, is energy. So picture me drawing these wavelengths on the board. So picture me taking my dry erase marker and slowly drawing that top wave there, the big wavelength. Then picture me taking my dry erase marker and drawing the short wavelength, up and down, 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 up and down. Okay. Think about which wavelength would have taken me more energy to draw. Yeah, the one with a smaller wavelength takes me more energy to draw, and it does in fact have a higher energy. So energy and frequency are directly related. So high frequency, high energy, low frequency, low energy. Okay. So we will come back to this idea of wavelength, frequency, and energy when we start talking about some experiments that scientists were doing. Couple more properties of waves before we dive into experiments. So the next two properties we're going to talk about are interference and diffraction. So the first one is interference. So interference is when we have, two waves that interact with one another or interfere with one another. So in this case, these two waves are kind of propagating out, and at some point they're going to meet up together. If those waves are in phase, what do I mean by in phase? Peak to peak, trough to trough, peak to peak. So if those waves are in phase, when they come together, we're going to call that constructive interference. Constructive interference means the waves get taller, the amplitude gets bigger. So what would we observe? How would we see that if we were looking at the light? This light would be brighter. So waves interfere, in phase, constructive interference. We get a bigger amplitude, brighter light. If two waves interact or interfere and they are out of phase, what does that mean? A peak and a trough, and a peak and a trough, and a peak and a trough. So they're kind of opposites. So if waves interact and they're out of phase, we have destructive interference. What is destructive interference? The amplitude gets reduced, or in this case, it just flatlines. It goes to zero. So when waves are out of phase, they interfere out of phase. We have destructive interference. Amplitude goes down. What would we observe? Well, we would observe this light either getting dim or going all the way black. So that amplitude would go down to zero. All right, so diffraction is the last property we're going to talk about before we dive into some examples. So diffraction is what happens when we introduce a wave to a slit. So before I get into what diffraction is, let me talk about these straight lines here. So these straight lines represent a wave. So let's say I dropped a rock right here into water. And then what you're going to see is the ripples of that water are going to start propagating out. And eventually those ripples are going to get so far away that they start to become straight lines instead of these like bent ripples. So the straight line portion of that wave, so it gets so far away from its source, the straight line portion of that wave is what you see in this slide right here. So this wave is propagated out. Now I introduce it to a slit. Diffraction tells me that the wave is going to bend through this slit, and this slit is going to act as a source, a new source for the wave. So we have this straight line propagating out, it bends through, and all of a sudden we restart those ripples. So diffraction is the bending of a wave through this slit. This is very different than what we would expect from a particle. So let's say I've got particles over here. So let's say I'm standing here. This would be fun. I've never had to draw this before. I always get to act it out. So let's say I'm standing here with a bucket of baseballs. And I start throwing the baseballs at this partition here. Okay? So I'm throwing my baseballs at the partition, and over here is some sort of detector. Okay. All right, so I start throwing the baseballs. One of two things is going to happen. I'm either going to hit the partition and the baseball is just going to simply fall back on the ground next to me. Or every once in a while, as I throw the baseballs, I'll actually make it through this hole. I'll actually make it through this slit. And it'll hit the detector over here against the wall. Okay. So when I have this detector over here against the wall, what I'm going to see is the baseballs that do make it through, we're going to see a lot of detections right here behind that opening. Any of the baseballs that hit this barrier and just simply fall are obviously not going to touch the detector. So I won't get any readings on this outlying area of the detector. It'll all be focused right in here. This is very different than a diffracted wave. So let's say I have that same detector right here for my wave. As this wave moves to the detector, we're going to see a series of places where that wave hits. It's not just going to hit in one central area. It's going to hit all along that detector. So that's very different than how a particle would behave when introduced to a slit, how a wave would behave when introduced to a slit. So detected all along the detector, particles, just this one area right here. So waves and particles, they behave very differently. I think we can all get on board with this. The last thing we're going to talk about, and this leads us directly into our experiment. This experiment is called the double slit experiment. In the double slit experiment, what scientists did is they took some sort of light source. So right here, we've got a source of light. They started to shine that light, and of course, light travels in waves, so the waves propagate out. Then they introduced that light to a barrier with two slits in it, double slit experiment. So what did the wave do through those slits? Well, it diffracted through those slits. So it bent through the slits and it essentially started a new wave. This acted as a new source. So we got a new wave here and a new wave here. Then we're going to let those two new waves propagate out, and then we're going to put a detector, eventually want them to hit a detector. As these waves are moving out, they're going to interfere with one another, right? They're going to interact with one another. So as these waves are moving towards the detector, we're going to get some of the waves that interact in phase, and we're going to get some of the waves that interact out of phase. So what we see right here is two waves that were in phase, amplitude went up, the light got brighter. Here we see two waves that interacted out of phase, so amplitude went down, and we see a dark spot. So this detector right here, the wide end is facing towards our experiment, and going from here to here, we just simply take that film and we lay it down. So just think about taking a piece of paper and then laying the piece of paper in front of you, and now you can see what's written on that paper. So what we see here from our detector is what we call an interference pattern. So we see light, or dark, we see dark, light, dark, light, dark, light. That's an interference pattern. What causes this interference pattern? Well, it's a wave that was out of phase, and a wave that was in phase, and a wave that was out of phase, and a wave that was in phase. So what this interference pattern tells us is that two waves went through the two slits, interacted with one another, and then hit the detector. So nothing crazy surprising there. That's exactly how waves should behave. We should see this diffraction or interference pattern. So how would you expect an electron to behave? Which way do you think it would behave? Do you think it would behave like a particle? Or do you think it would behave like a wave? Let's see. What we see here is something called the Hitachi experiment. So in the Hitachi experiment, what scientists were doing is they were really just trying to show off their new skill set. Pause this real quick. So they had this brand new equipment. The equipment could throw one electron at a screen at a time. They weren't trying to really discover anything. They weren't trying to find this new theory or anything like that. They were really just trying to show off this new instrument that they built. So they said, hey guys, look, I can take one electron at a time. I can throw it at a screen and I can detect that one electron at a time. Isn't that fun? Let's watch. So they did this in the manner of the double slit experiment. So what they're doing here is they have a barrier. The barrier has two small slits in it. They're taking an electron and they're throwing it through those slits one at a time. And I want you guys to see what happens. So one of the first things you'll notice is that those electrons aren't hitting right behind the barrier or right behind the slits, right? They're hitting all over the screen. Well, how the heck would a particle go through a slit and then hit on the left-hand side of the screen? We don't know. Let's keep watching. Okay, anybody see it yet? So what do we see here? Yeah, we see those lines. We see an interference pattern. We see dark, light, dark, light, dark, light, dark, light, dark, light, dark, light, dark, light. That's an interference pattern. So what did the Hitachi experiment tell us? It told us that electrons behave like waves. That's odd. Huh. Thought electrons were particles, not waves. Weird. So here we see two different experiments. We'll come back to this idea of what a photon is. But here's the results of the Hitachi experiment. So doing this double slit experiment with electrons. And here's the result of doing the double slit experiment with light. So both of them create interference patterns. Both of them behave as waves. Perfect. So electrons aren't actually particles. Electrons are waves. Easy. Not so fast. The next experiment we're going to talk about is going to prove to us that electrons behave like particles. Welcome to quantum mechanics. So first, let me set up this experiment. So photoelectric effect. The photoelectric effect says when you hit a piece of metal with light, if it's the right kind of light, the light will hit that piece of metal and boom, it'll eject an electron. So that's the photoelectric effect that just happens. Metal emits electrons when it's hit with the right kind of light. Okay? Binding energy, so again, nothing you're going to be tested on, just hopefully will aid in your understanding. Binding energy is the amount of energy needed to dislodge that electron. So I have to hit it with enough binding energy to boom, dislodge that electron. If I don't overcome the binding energy, electron's not going to go anywhere. So just kind of something to help you picture this a little bit better. All right. So, prediction. Up until this point, we were trying to use classical physics to explain the behavior of electrons. So classical physics is very predictive. It can tell you what's going to happen, how it's going to happen, as long as all of the conditions are the same. So it's a very predictable science. So predictions that were made. If electrons do in fact behave like particles, we predict that the higher the amplitude or the shorter the wavelength, the easier it will be to knock electrons off. And I just misspoke. If light behaves like a wave, if light is a wave, the higher the amplitude, the shorter the wavelength, the easier it will be to knock off electrons. So let's think about this with something that we can picture. So what does a higher amplitude tell me? Well, higher amplitude is a more intense light, a brighter light, right? So if I shine a really bright light on that metal, boom, those electrons will knock off. Okay? Low amplitude or low energy light would cause a lag time. So what this is saying is that if you don't have enough intensity when you first hit that piece of metal with light, you could keep tapping on that piece of metal and eventually that electron would come off. Okay? So let's think about baseballs. So I have a bat. If I take that bat and I whack that piece of metal with a lot of intensity, if I whack that piece of metal as hard as I can possibly whack it, yeah, an electron's going to pop off. Or if we think of baseballs, yeah, a baseball's going to pop off. Okay? Or I can take that same bat and I can hit it with a lighter intensity. So just kind of tap on that piece of metal. And eventually, if I keep tapping long enough, that electron or baseball is going to wiggle its way off that piece of metal and it's going to come off. So those are two things that would be pretty easy to picture happening, right? So if light is a wave, a nice smooth wave, this is how things should behave. But what actually happened? So let me talk you through this table first, and then we'll talk about how this did not go with our predictions. So here along the bottom, we have frequency of light. So over here on the left, the frequency would be 0. Over here on the right, we would have a high frequency light. So high frequency, high energy. Here we see the rate of ejection of the electrons. So down here at the bottom, no electrons are coming off. Up here at the top, all the electrons come off. Okay. So what this is telling us is that I am going to hit the piece of metal with a low frequency. So low energy, low energy, low energy, low energy. Boom! I hit the perfect energy and all the electrons came off. Okay. So what does this results? What does this data tell us? This data tells us that it is independent of amplitude. It doesn't matter if I shine the brightest light or the dimmest light. If it is not the right frequency, it is not going to eject an electron. Okay? So if I use a light down here that's really bright, really intense, I hit it as hard as I can. It is not the right frequency of light. So no matter how hard I hit it, those electrons are not coming off. And then when I get up to here, once I hit this perfect frequency, I hit the correct frequency, it doesn't matter how hard or how soft I hit that piece of metal. As long as I'm using the correct frequency, all the electrons are going to come off. Okay? So I could tap it and I'd have all the electrons come off. I could hit it really, really hard and still all the electrons are coming off. So independent of amplitude, it doesn't matter how hard you hit it. What it does depend on is frequency. Are you using the correct bat, essentially? So it's dependent upon frequency. Duration is also not a factor. If I'm using the wrong bat, it does not matter how long I sit there and hit that piece of metal. Those electrons are just never going to come off. Okay? So duration was not a factor. It didn't matter. You just had to have the correct frequency, that threshold frequency. Okay. So what this tells us is that we cannot use classical physics to explain the behavior of electrons. We cannot even use classical physics to explain the behavior as light. I do one experiment. Electrons and light behave as waves, double slit. I do another experiment. An electron and light behave as particles. Photoelectric effect. So what is it? Is an electron a particle or is it a wave? Is light a particle or is it a wave? What's going on here? This is where classical physics starts to fail us. This is where the classic Newtonian physics starts to break down. You know, when I put a picture of Einstein in here, things are about to get serious, right? So Einstein proposed that instead of light being this nice, smooth wave, instead, light travels in these little packets of energy called photons or quanta. So now we're starting to get into quantum mechanics here. So lights travel in these little packets of energy called photons. Light is lumpy, he said. Photons and electrons behave like each other. So are they waves or are they particles? The answer is yes. They're both. Welcome to quantum mechanics. Welcome to chemistry. Things are getting serious. So an electron's behavior can be described as the following. It has a particulate nature to it. So electrons and light do behave like particles sometimes. Electrons and light also have a wave nature, so they behave as waves sometimes. Okay. This is called the wave-particle duality. So they contain properties of both. These properties are complementary properties. So the more that I study the wave characteristics, the less I know about the particle. And the more I study the particle characteristics, the less I know about the wave. So that's what makes electrons and light so difficult to study, is they have wave and particle nature, and it's hard to study both of those natures at the same time. So what we needed was this new realm of physics that could encompass both of these natures into one. So we needed another category of physics that maybe wasn't so easy to predict things in. Okay. Another note that I like to make here is, so people like to say, well, is an electron a wave or is an electron a particle? And you can't really break it down like that. You can't say either or, yes or no. So a chicken, for example, is a chicken a bird? Yeah, but it doesn't fly. Is a chicken a duck? Well, they kind of walk the same, but it's not a duck and it's not like a flying bird. What is a chicken? Well, a chicken is a chicken. A chicken acts like a chicken. It doesn't act like a duck. It doesn't act like a pigeon. It acts like a chicken, right? Electrons are the same way. You can't say an electron behaves like a particle sometimes and a wave sometimes. An electron behaves like an electron. And when you fully grasp that concept, it gets a little bit easier to know an electron. An electron is an electron, and it's weird. It's really, really weird, but that's how we're going to study it. So how do we study electrons? Obviously, classical physics isn't going to work. So classical physics is very deterministic. If I hit a baseball with the same force, the same trajectory, the same velocity, it's going to fall in the exact same position every single time. I can predict that. Electrons, you cannot. Okay? So quantum mechanics was born. In the early 20th century, scientists began investigating absolutely small world of matter, this quantum world of matter. These were some big name scientists: Einstein, Schrödinger, Niels Bohr. So names Heisenberg, names that you've probably heard about before. So this was a big time push that was going into quantum mechanics. Their work laid the foundation of our current understanding of matter and subatomic particles. So they were kind of the grandfathers of this quantum mechanics, this new realm of physics that is alive and well today. Okay. So predictive versus probabilistic. So for classical physics, we had this very predictive line. If I hit a baseball here, it's going to land here. Quantum mechanics is not based on facts and predictable manners. Quantum mechanics is based on probability. So if this is an electron and that electron moves, I can't say that it's going to move from point A to point B along this line. What I can say is it's going to move from point A to point B, and during the process, it's going to be somewhere in this probability map. It's going to be somewhere inside of these dots. And I'm really, really certain, I can't tell you exactly, but I'm really, really certain that somewhere it's going to be in there. That's how we study electrons. We cannot know their position, velocity, location, but we have a pretty good idea of where we are likely going to maybe find them. At this point, I think it's a good idea to go ahead and dive into your lab. So the lab this week is a video. So you're going to watch a quantum mechanics video and fill out a response sheet as you're watching the video. I think the video does a great job of kind of tying everything together that we just talked about. And they do a better job with animations and that sort of thing. So now would be a great time to go ahead and tackle your lab. And that ends this video. The next video, we're going to dive into, okay, we have this probability map. Where are electrons at? How do we know where an electron is around that nucleus? So stay tuned for that.